Welcome to this video on embedded domain walls and electroweak baryogenesis. This is a project I've been working on in collaboration with Robert Brandenberger from McGill University. In this talk and the corresponding paper, we will present a way to explain the overabundance of baryons over antibaryons observed in our universe. This overabundance of matter over antimatter can be quantified in terms of the baryon to entropy ratio. This is nowadays well constrained by CMB and BBN observations to be a value of 9 × 10⁻11. Any mechanism producing such an overabundance of baryons needs to satisfy 3 criteria, the so-called Sakharov criteria. The mechanism needs to be baryon number violating, it must happen out of thermal equilibrium, and it must violate C and CP symmetry. One such mechanism that satisfies these 3 criteria is electroweak baryogenesis via a first-order electroweak phase transition. The idea is as follows. At the electroweak phase transitions, bubbles of the broken phase nucleate within the symmetric phase and expand then with relativistic velocities. If one introduces, for example, a 2 Higgs doublet model with a CP violating relative phase between the 2 Higgs doublets, then matter and antimatter will be reflected in a CP violating manner from this bubble wall. This leads to the development of a chiral asymmetry in front of the bubble wall, which can then diffuse into the symmetric phase. Since in this unbroken phase, Weeks-Faleron processes are unsuppressed, they can convert the chiral asymmetry into a baryon asymmetry. A very similar mechanism is defect-mediated baryogenesis. It does not require a first-order electroweak phase transition, but instead cosmic defects in which the electroweak symmetry is restored. In addition, one needs again CP violation at the defect wall. If the defects move now with relativistic velocities with respect to the cosmic fluid, then fermions will be reflected in a CP violating manner from the wall. This leads to the injection of a chiral current into the interior of the defect, where Weeks-Falerons can again convert the chiral asymmetry into a net baryon number. The ideal defect to realize this would in principle be a domain wall. The problem with domain walls is that they overclose the universe. Therefore, one typically realizes the mechanism with cosmic strings, which reach a so-called scaling regime. This means that the energy density of the cosmic string network becomes a constant fraction of the critical density and therefore does not overclose the universe. If we assume that in both scenarios, either with strings or with domain walls, we have roughly the same number of defects per Hubble volume, then the baryon to entropy ratio produced in the string scenario will be suppressed by a factor of the string width divided by the Hubble length in comparison to the domain wall scenario. In the following, we propose a scenario of embedded domain walls which are stabilized by plasma interactions. Since we have domain walls, they don't come with a dimensional suppression of cosmic strings. On the other hand, since they are stabilized by plasma interactions, they will decay once the plasma interactions become ineffective and these embedded domain walls don't lead to an overclosure of the universe. After this short introduction, I will give a brief review of the idea behind embedded defects. I will afterwards show how one can compute the baryon to entropy ratio from non-local electroweak baryogenesis via embedded walls. In the fourth part, I will come to the main point of this talk, which is the introduction of a particle physics model that contains embedded domain walls in which the electroweak symmetry is restored, and finally, I will discuss our results. Let us start by reviewing the idea of embedded defects. A simple example is already contained in the standard model, namely the electroweak Z-string. If we consider the electroweak Higgs and call it phi, we can write it in terms of 4 real scalar fields phi naught to phi 3. The zero temperature Higgs potential is then of this well-known form in equation 2. As one can easily see, The minimum of this potential is a 3-sphere, and therefore we can say that the vacuum manifold has a topology of a 3-sphere. This means that this theory does not allow for topologically stabilized defects. Due to this potential, starting from the symmetric phase, the Higgs will acquire a non-vanishing vacuum expectation value and break the electroweak symmetry to the U1 symmetry of electromagnetism. One can then easily calculate the charges of the different Higgs field components under U1 electromagnetism. One finds that the Higgs consists of 2 electrically charged real scalars, let's call them phi1 and phi2, and 2 uncharged scalars, let's call them phi0 and phi3. After electroweak symmetry breaking, photons will interact only with the charged field components phi1 and phi2. Interactions with thermal plasma then introduce an effective contribution to the potential of the Higgs, which is of the form written down here in 4. This means that the effective potential is lifted now in the charged field directions, but not in the uncharged field directions. Correspondingly, the effective vacuum will change, and as it turns out, it changes to a circle and is no longer simply connected. This means then that electroweak strings are stabilized via plasma interactions. For a baryogenesis scenario, we want, however, embedded domain walls which require a disconnected effective vacuum. In a toy model, this can simply be realized with a Higgs field consisting of 3 real scalar fields, phi0, phi1, and phi2, and a vacuum manifold which has a form of a 2-sphere. If now the fields phi1 and phi2 are again electrically charged, but phi0 is not, then plasma interactions will lift the potential in the phi1 and phi2 directions and not in the phi0 directions, and the effective vacuum becomes disconnected, and we obtain plasma-stabilized embedded domain walls. Later on, we will see a particle physics model where this is actually realized. Next, I want to explain how a baryon asymmetry is obtained via non-local electroweak baryogenesis with domain walls. For this, let us consider a domain wall after the electroweak phase transition, such that outside of the wall the electroweak symmetry is broken, but inside of the wall the electroweak symmetry is restored. The domain wall will then move with a velocity vd with respect to the plasma. We can then introduce a 2 Higgs doublet model with a relative angle between the 2 Higgs doublets in such a way that left-handed particles and their CP conjugates have different reflection coefficients and different transmission coefficients. Looking, for example, at the difference between the reflection coefficients, one finds that it is proportional to the change of the relative angle over the boundary of the domain wall, which is denoted here theta CP. This chiral asymmetry will then lead to the injection of a net left-handed fermion current, J0, into the wall. While outside of the domain wall, Weeks-Faleron processes are exponentially suppressed, inside of the wall they are unsuppressed and can convert the chiral asymmetry into a baryon asymmetry. The corresponding conversion rate is expressed in equation 7. Here we have, for example, NLL, which denotes the net left-handed lepton number density, that is, the number density of left-handed leptons minus the number density of their CP conjugates. NBL is a similar term for left-handed baryons. On the left-hand side, we have the net baryon number density, that is, baryon number density minus antibaryon number density, and we have a conversion rate which is proportional to the Weeks-Faleron rate. For this kind of baryogenesis mechanism, one found in the past that the main source are tall leptons. Therefore, we will focus in the following on the injection of left-handed leptons only. Solving the diffusion equation with J0 as a source term, one finds for the net density of left-handed leptons across a wall the expression given in equation 8. Here, d is the diffusion constant and z is the coordinate in the direction perpendicular to the wall. Using the conversion rate of left-handed leptons into baryons from the previous slide, we can calculate the net baryon number density produced while the wall sweeps over one point, and find the result given in equation 9. The prefactor NB0 is here proportional to the injected left chiral flux J0. Evaluating this expression for temperature of the order of a Higgs mass and theta Cp of the order 1, one finds that the baryon to entropy ratio gives a value of 10 to the minus 11. This value is compatible with the measured baryon to entropy ratio, even if only marginally so. The previous calculation assumed that domain walls swipe over each point in space only one time. In reality, we will, however, not obtain a single domain wall, but an entire network of domain walls with a few walls per Hubble volume. The walls can then swipe over each point in space multiple times. Let us more quantitatively express the baryon to entropy ratio after the domain walls have passed each point in space n+1 times. The first term is due to the baryon to entropy ratio that remained after the nth passage of the domain wall and then is again diluted by electroweak Fallon processes. On top of this, we have to add the second term, which is the newly produced baryon to entropy ratio. Using this formula, we can either estimate analytically or calculate numerically the enhancement due to multiple passages of domain walls over each point in space. Assuming a number of order 10 domain walls per Hubble volume and relativistic velocities, this enhancement can be as large as 10 to the 2. Therefore, the presented mechanism can comfortably explain the observed baryon to entropy ratio. All of this is interesting, but doesn't help us if we cannot find a particle physics model which gives rise to embedded walls. In the following, I want to present a way to construct such a model. To this end, I want to include the standard model symmetry group into a larger symmetry group G. The model should not contain stable domain walls, but only walls which are stabilized via interactions with an electromagnetic plasma. The electroweak symmetry must furthermore be unbroken inside of the wall. As I will show in a moment, this can be achieved by considering the gauge group given in equation 12. The difference to the standard model symmetry group is that we don't have the U1 weak hypercharge group, but instead an SU2A cross U1B group. To obtain embedded domain walls in our model, we need to realize a symmetry breaking to the standard model in two steps. First, we break the group SU2A cross U1B with a Higgs field phi to U1A cross U1B, and then with another Higgs field psi to the weak hypercharge group U1Y. We can do so by choosing phi in the triplet representation under SU2A and trivial representation under all other subgroups, as well as psi as a doublet under SU2A and with charge 1/2 under U1B and transforming trivially under SU3C and SU2L. We can write phi in terms of three real scalar fields, phi 1 to 3, here contracted with the corresponding generators T1 to T3, and we can write the Higgs doublet psi in terms of two complex scalar fields psi1 and psi2. Let us now start with the first stage of symmetry breaking, where we break SU2A to U1A. We can do so with the potential for the Higgs triplet as given in equation 15. As one can see from the explicit form of the potential here, the minimum of it is described by a two-sphere, which is correspondingly the vacuum manifold. Such a vacuum typically gives rise to monopoles and not domain walls. As we will see, plasma interactions will, however, change the vacuum in such a way that the effective vacuum stabilizes domain walls instead. Due to the form of the potential below the symmetry breaking scale, the Higgs field phi will acquire a vacuum expectation value. We can choose our three axes in group space in such a way that it points along the vacuum expectation value, and this VEV is given by expression 16, where T3 is the unbroken generator. Symmetries corresponding to the other two generators, T1 and T2, are broken. The remaining U1A cross U1B subgroup then acts on the second Higgs field, in this way given by equation 17. We can now realize the second stage of symmetry breaking with a field psi, again with a quartic potential of the form given by AT. To ensure that either psi1 or psi2 acquires a vacuum expectation value and the U1Y subgroup remains unbroken, we need to introduce an additional interaction between the Higgs field phi and the Higgs field psi. An expression as given in equation 19 will do. Due to this, the potential of the Higgs field psi becomes, after the first symmetry breaking, effectively of the form given in equation 20. Here we introduced μ1 and μ2 and will assume that the parameters are chosen in such a way that μ1 and μ2 are larger than 0. In this case, the prefactors of the quartic and the quadratic term of the psi1 field are both positive, and psi1 will not acquire a non-vanishing vacuum expectation value. For the psi2 field, however, the quartic term has a positive prefactor and the quadratic term has a negative prefactor, which means that the vacuum expectation value will not be at psi2 equals 0. More precisely, we know that the vacuum expectation values are in such a way that psi1 is equal to 0 and psi2 will be equal to v psi. So we can choose the vacuum expectation value of the doublet psi to be of the form given in equation 21. Going now back to the previous slide, where we had the transformation behavior of the Higgs doublet, we can see that transformations which have alpha 3 equal to beta will leave this vacuum expectation value unchanged. Therefore, we have a diagonal subgroup which leaves psi2 untouched and is therefore unbroken. The unbroken U1 subgroup can be identified as the symmetry group of weak hypercharge with a corresponding weak hypercharge operator, which is simply the sum of the charge under U1b symmetry and the unbroken generator of the SU2a symmetry. With this, we can come to the third and last stage of symmetry breaking, which is the electroweak symmetry breaking. We do this with the usual Higgs doublet. This Higgs doublet is a singlet under SU3C and SU2A and a doublet under SU2L, and to get the weak hypercharge correctly, it has to have charge QB 1/2. The symmetry breaking can be obtained as usual with a quartic potential given in equation 23. For the remaining U1 group of electromagnetism, one finds the electric charge operator expressed in the form 24 down here, where Tr3 is an unbroken generator of the SU2L symmetry. With this operator at hand, we can now determine the electric charges of the different components of the Higgs field phi. To this end, we can rewrite phi in terms of phi plus and phi minus, which have well-defined electric charges, and we find that phi plus has charge 1, phi minus has charge -1, and phi 3 is uncharged. After electroweak symmetry breaking, the only remaining massless gauge field is the photon. We can now apply thermal averages to the photons. Under these averages, terms linear in the photon field will go to 0, while terms quadratic in the photon field will be proportional to the temperature squared. The important point is now that due to the different charges of the components of the Higgs field, mu will only interact with the charged components phi plus and phi minus, or equivalently phi 1 and phi 2, but not with phi 3. Looking at the kinetic term of the Higgs field phi, one finds that it contributes to the effective potential. This contribution to the potential, which is written down here in equation 27, is basically the same as we had seen previously for the electroweak Z-string. Due to this, the potential of the Higgs field phi is now lifted in the directions of the phi 1 and 2 components, but not in the direction of the uncharged phi 3 component. The effective vacuum becomes, due to this, disconnected. Previously, we had a vacuum manifold S2, now we have an effective vacuum manifold S0. This tells us that we have achieved our goal and found embedded domain walls which are stabilized by plasma interactions after the electroweak symmetry breaking. To get exactly what we want, there is, however, one thing still missing. So far, electroweak symmetry is still broken inside of the domain walls. To restore electroweak symmetry inside the domain wall, we need to introduce interactions between the Higgs field phi, which makes up the domain wall, and the electroweak Higgs field H. An interaction that serves our purpose is given by equation 29. We can see that outside of the domain wall, where the Higgs field phi acquires its vacuum expectation value, this term here vanishes. Therefore, the potential V phi is equal to 0, and the electroweak symmetry is broken as usual. Inside of the domain wall, however, phi is equal to 0, and V4 takes on the value given here. We can then consider the full electroweak Higgs potential inside the wall after the first symmetry breaking, which will be given by the expression 30. If the prefactor in front of the quadratic Higgs term is now positive, then the electroweak symmetry will be restored inside of the domain wall. With this, we have provided a particle physics model that gives rise to embedded domain walls, which are stabilized via plasma interactions after electroweak symmetry breaking, and in which electroweak symmetry is restored. Finally, let me now come to the discussion and summarize our results. We have seen that electroweak baryogenesis with a network of embedded domain walls can explain the measured baryon to entropy ratio. Compared to electroweak baryogenesis with a first-order electroweak phase transition, we get an enhancement because domain walls can wash over each point in space multiple times. In a first-order electroweak phase transition, the bubble wall can do so only once. In comparison to string-mediated baryogenesis, we get an enhancement because strings wash over a much smaller volume of space than domain walls can do. While this would not be possible with stable domain walls, which lead to overclosure, embedded domain walls become unstable once the plasma interactions are inefficient, and therefore this scenario does not lead to overclosure. The decay process of embedded domain walls is something that needs to be carefully studied in the future. In addition to this, the baryogenesis mechanism presented here can be applied to other domain walls which decay, such as biased domain walls and metastable domain walls. If you're interested in the details and would like to learn more, then please take a look at our paper on arXiv. Thanks for watching.